For our next example, we're going to calculate the Laplace transform of T. Once again, we're going to use the Laplace transform definition with the integral. All right, and when you first look at this integral, you'll notice that it just can't be found directly, so we're going to use integration by parts to find it. And we'll take a look at using the u as the t, because again, the idea is we want to differentiate this to make it simpler. Then we'll let the dv be the exponential part, because that's easy when we integrate it. It doesn't get more complicated. So u will be equal to t. Du is then equal to dt. dv is e to negative st dt, integrating negative 1 over s e to negative st, like we saw in the previous example. Now putting this all together, we're going to have then the first part is u times v, so that's negative t over s e to negative st from 0 to infinity. Now minus the integral from 0 to infinity of v du, which is going to be just our negative 1 over s e to negative st dt. All right, and we'll save that first piece for later, so we want to make sure we go ahead and integrate the second term first. So that's negative t over s e to negative st. And now we're going to have yet another minus. We get another factor of s. And we have e to negative st. This is now all evaluated from 0 to infinity. All right, now we're going to go ahead and use the limit definition. So this is equal to the limit as t goes to infinity of negative t over s e to negative st minus 1 over s squared e to negative st, again from 0 to t. And we now go ahead and evaluate this. Limit t goes to infinity of negative capital T over s e to negative s times capital T minus 1 over s squared e to the negative s times capital T, and then minus, when we evaluate at 0, negative 0 over s e to negative s times 0, and then minus 1 over s squared e to negative s times 0. All right, and then just like before, we're going to have both of these first terms go to 0, because again, the idea is that exponential functions decay faster than polynomials, which is the first term. So this one goes to 0 if s is greater than 0, and likewise, this goes to 0 when s is greater than 0. And again, it's actually the term, so fix that. All right, so another thing to say here is if you didn't like just the hand-waving argument for this, you could also use L'Hopital's rule to argue that this first term does go to 0. Now, that last term back there, that just is equal to 0. And then we have one term left. We have the opposite of negative 1 over s squared. That simplifies down to just 1 over s squared when s is greater than 0. So we've shown the Laplace transform of t is just 1 over s squared when s is greater than 0. At this point in time, it's kind of good to think about what would happen if you looked at t squared or t cubed or any power of t that's a whole number. And we'll talk about that in the guided notes coming up next.